Okay, so let's get started. So we have seen that in the previous coin, which is Goofy's coin. So we have the problem of double spending because the transactions are not publicly visible, right? So because there is no way people can know about the other transactions. So that's why LS was able to create a double spend problem. So now we are looking into Screwy's coin, a simple design, where we try to solve this the double spending problem by having all the transactions publicly visible, right? So again, we have some simple rules. The first key idea is that Squeeze can create transactions, can create coins because he is the owner of the currency, let us say. And what he does is he creates coins and he transfers to the people and things like that. On top of that, he will also keep track of the transactions. So for example, in the previous case, when LS has created a transaction, transferring coin to the Bob, and that will be sent to Squeeze, and he will put it into the block, you can say here. And then what he does is he will put it into the block and he will prepare a hash pointer. Let's say that he prepares a chain of blocks, you can say, and each block contains a transaction like what LS has done previously. And he will link the blocks using the hash pointer. Again, why hash pointer? It gives us the property of append-only ledger, so that means nobody else can change it. On top of that, to prove that these blocks are valid, he will sign the hash pointer every time when he creates a new block. So what I mean to say is, whenever he creates a new block, he will create a hash pointer. So take the hash of the latest block, and he will sign with his private key so that it is authenticated, you can say, and he will publish this hash pointer at a public place. Either it could be a newspaper or whatever it may be, or some place where people can see it. Right. So that is the main thing. So how the append-only ledger is implemented. So basically, to implement append-only ledger, Shrewis will build a chain of blocks like what I have mentioned. And for the sake of simplicity, assume that only one transaction in the block and things like that. And what is a block? It contains some information, some ID, and transaction contains some information saying that the value of the coin to which a coin is transferred. In the previous case, LS has transferred to Bob, right? So all that information will be part of the transaction. And remember that he signs, Squeeze digitally signs the final hash pointer so that it is valid, right? So it is valid. And why do we want him to sign the transaction? Because we want to make sure that he's the only one who created this block, right? Otherwise, somebody else, maybe a eavesdropper, can create a block and add it to the blockchain, and we don't want that to happen because he is the custodian of the currency. Okay, so let's see how the transactions are verified, right? Whether we are able to avoid the problem of double spending or not. So in Squeeze coin, in this design, a transaction is only valid if it is in the blockchain signed by the Cruise. We know that Cruise is the one who is keeping track of the transaction, and the way to verify the transaction is to see whether the transaction exists in this block of chain, in the chain of blocks or not, right? So for example, again, bring back this previous scenario where LS has transferred the coin to both Bob and Shook. So the way Bob verifies is, Bob will immediately go to this ledger and see if this transaction is if the transaction is valid or not. Then only he will believe that, okay, this coin is transferred to me, right? So there is an extra step where the transaction is officially put onto the blockchain. Let's say that now LIC is trying to create a double spend transaction, and she create a transaction transferring to the same coin to Chook. Then what happens? Then Chook will also do the same verification step. He will go to the blockchain and see if this coin is already being spent, right? If it is already being spent to already being sent to Bob, the transaction will be part of this chain. So then Chuk will immediately identify that Alice is trying to cheat him. She is trying to transfer him a coin which is already transferred to Bob, right? So that is the main advantage of this design. So since the transactions are publicly verifiable, so anybody can see whether a transaction is double spent or not, right? Anybody can verify the Screws endorse the transaction by checking the Screws signature. And how do they believe? Each block is signed by the Screws signature, and people will believe Screws because he is the custodian of the currency, like a bank or like the Reserve Bank of India and things like that. So if he says valid, then it is valid. And for the time being, let's assume that Screw is honest and he doesn't endorse the double spend transactions, right? So that is also an issue. But for the time being, just assume that he doesn't do all sorts of things. So the transactions are, he will only put the transaction into the blockchain if it is valid, if it is not double spent, right? Okay. And again, let's get back to this append-only ledger because it is one of the foundation for the Bitcoin as well. In Bitcoin as well, in most of the blockchains, we use some kind of append-only ledger semantics, right? Why do we need a blockchain with hash pointers in addition to having the screws to sign each block? So my question is, why do we need this kind of linking between the blocks? Because each block is signed by screws, right? And why do we need this kind of structure? Is it not sufficient since each block is signed by screws and he is the custodian of it? If he signs the block, that should be sufficient, right? Why do we need this extra step of hash pointers? Can anybody can answer that? What advantage do we get by having this extra structure, data structure, where hash values are taken of the previous blocks and put as a hash pointer in the subsequent block and things like that? What advantage does it give us? Because we believe Cruz, so he can simply, and each block is signed by him. And to verify whether the transaction is valid or not, we look into the block. And if it is signed by Screws, then it is validated. And why exactly do we need this kind of hash structure? And what advantage does it give us? Anyone? So let's see, there is some chart somebody put. To extract information quickly and efficiently when needed. Yeah, not exactly. So anyone else? So it some kind of partially true, but not very much. Because let us imagine that we don't have any hash pointers in the blockchain, right? So then you just go to the blockchain, verify whether the transaction is exist or not, right? So you are actually performing more work every time checking whether the hash pointer is valid or not. So in that way, other design is not efficient and quick. So there is something else which actually gives this the additional strength and things like that. Let's think about this scenario, right? I was saying that Screw is honest and things like that. Let's say that what happens if Screws want to meddle with some transactions. Let's say that we have this block containing 71, and let's imagine that now there is LIC is the friend of Screws, and both LIC and Screws they collided each other, and now he want to meddle the transaction, change the transaction and other kinds of things. Right? In the design where you don't have any hash pointers, he can simply do it because he all the blocks are signed by him. So he can sign the block. He can go to the block number 71 and he can change the transaction and he can simply sign it. That is perfectly valid, right? So in a ledger where we don't have hash pointers, he can simply change the transactions and he can sign it because we believe his signature and he can simply sign it without any big problems, right? Of course, it's another thing. It's a different thing whether he will be honest or he is whether why do you want to do it and things like that. But let's imagine that in the previous design, he can simply change the transaction or modify the transaction and re-sign it, and people can buy that, right? But having the hash pointers will offer one extra flexibility. Let's say that what I was saying is whenever the block, let's say this block is created, now a new block 73 block is created. I was telling you before saying that each time when the block is created, the hash of the block is taken and it is signed by the squeeze with private key, and then it is published somewhere else, right? Since the blocks are being produced on a continuous time, so you will have the signature, hash-based signatures by squeeze all the time. And in case where we have the append-only ledger with hash pointers, let's say in this design, what happens if the squeeze want to be malicious and he want to help Alice and he go to the block and change the transaction? Now we are in the append-only ledger. What will happen then? Can anybody say? What advantage does it give us? Or let us say that if Screws modifies the transaction in the block number 71, how does people will identify that in the design of the append-only ledger where we have the hash pointers? Okay. No clues? Okay, let me tell me whether it is possible to identify if Screws changes the transaction in the block number 71 in the append-only ledger or not. So in the previous scenario where we don't have hash pointers, I was saying that he can change the transaction and he can simply sign it, and people can easily buy it because it is signed by him. But now having this hash-based pointers, now what I'm saying is, let's say that he goes back and changes the transactions, modifies the transaction in the block 71. Is it possible to identify or not? I'm saying that it's possible to identify, but how? That is the question which I'm asking. How do we identify? Okay. No solutions. So that means you are not with me or you are not following. Okay. Let me tell what happens here, right? So every time we create a block, we take the hash pointer. That's how we create the hash of it. We take the hash pointer and signed by the cruise and publish it somewhere else, right? So for example, in case of append-only ledger, let's say that all these hash values have been produced on a continuous time or a regular intervals and published with the signature of the screws and things like that. Now let us imagine a scenario where Cruz will go back to the block 71 and he tries to modify a transaction. Then let's see what happens, right? If he changes a transaction in the block number 71 and the size of the block will change, you can say the block now it is the same, not as the same as the original block. Now, since something has changed, So the hash value of the block will be new value, and this hash pointer will not be valid, right? So remember, people in the append-only ledger, the hash pointers were published publicly with the Scrooge signature, and anybody can verify that, okay, Scrooge did something messed up with the transaction. Otherwise, this hash pointer should be valid. But now when I try to take the hash of this block, now it is getting a different value, but the original hash pointer is different value, right? So this hash pointer will not be valid. So that's how we identify if he tries to modify the transaction. You might argue that, okay, since he is the one who is signing the blocks and creating the blocks, what will stop him from changing the transaction in the block 71 and creating the hash pointers and putting all the blocks and re-signing all the blocks? Of course, he can do it, but he will be caught because these hash values have been published regularly, right? People can see that now blocks are with different hash values, so that means there is something happened or somebody has meddled with the data. So that is why append-only ledgers are quite they offer a very good functionality of tamper resistance, right? So as long as somebody monitors the latest hash pointer, for example, if I want to make sure that the blockchain is intact without any tampering of the data, I just need this latest hash pointer. If I have the latest hash pointer, I can go here and take this block and hash it and see if it tallies with the hash, then the block is good. Then from here, I go to this previous block and take the hash value of the block and then see if the hash pointer and the hash value is both are the same, then the block 72 is also valid. And I go here, again, I do the same check. Suppose, for example, if Scrooge has meddled with the data, and if I take the hash of this block, this hash of the hash value of the block will be completely different than what is recorded here. Then I can simply identify that, okay, somebody has meddled with this data. And since in this design, only Scrooge can design the blocks, so we can identify that Scrooge has changed the data in the block 71. So that is the advantage of the hash pointers which we get. So in the systems where Scrooge signs the blocks individually, you'd only need to keep track of the signatures from the Scrooge and also the latest hash pointer that will validate all the blocks from the beginning to the end, right? So how do so if you keep track of the latest hash pointer, and that should be sufficient, and two individuals can independently verify the transactions or the history of the transactions is the same or not, right? So that gives us the append-only ledger this time. Okay, any questions on that?
No, sir.
Okay, so yes, let's go further. Let's look into the transaction semantics, right? Like, so we have two types of transactions in this Scrooge coin. The first one is the create coin transaction, like in case of the Goofy coin, where the owner of the currency can create coins. In this case, Goofy can create coins. And the second transaction is pay coin transaction, where coins are transferred from one person to other and things like that. So create coin is just like Goofy design. So basically he creates and signs. So that's how the new coin is created. We will extend with the Scrooge coin a bit detail. So let's look into the create coin transaction. So this looks like this. So each transaction has multiple the serial numbers, you can say. You can have multiple coins created in the create coin transaction. So that means in this case, we are creating 3 new coins and they can have different values. So first one is 3.2 and the last one is 7.1 coins and things like that. And we also have the recipient address, right? So see, this is nothing but the same as the K-coin transaction, but to be more flexible, now we are creating multiple coins in the create coin transaction. right? So that's the only change. Each coin has recipient, which is nothing but the public key to which the coin is transferred. Okay, so this is how the create coin transaction looks like. So you have the transaction ID, a unique ID for the transaction, because we are putting into the block and things like that. So we keep track of all the IDs, unique ID for each transaction. And since this is a create coin transaction, we create new coins. Let's say we are creating 3 coins, and we have the value of the coins, and we have the recipient. Yeah. Hello? Yes, go ahead. Is there any question? Okay. So yeah, we create the transactions like this. And since Goofy signs the, Scrooge signs this transaction, so this is valid because he's the one who creates the transaction, right? Like who creates the coins and things like that. So now let us look into the pay coin transaction. So the purpose of the pay coin transaction is to transfer the coins from one to another. So let us say we have again a transaction ID with the serial number, and the type is pay coins. But what we have here is we have a series of coins which are being spent. So for example, in this transaction, I am consuming 3 coins, 68.1, 42.0, and 73.2. What are they? These are nothing but the coins created here. So, let me go back one step. So how do we identify the coins, right? So let us say that the coins are identified with the coin ID, which is nothing but a combination of the transaction ID and the index of the coin, right? So for example, if I want to identify the transaction, if I want to identify the coin where the value is 3.2, so the first coin, I name the coin. I use the coin ID as 73.0. 73 is the transaction where the coin is created, and this is the 0 is the zero-based index. So I can see that okay, this coin is created in the transaction ID with 73, and since 0 we have 0, so this is the first coin created in that transaction, right? Similarly, the last coin is identified as 73.2. So basically, again, the transaction ID and the serial number of the coin. So we use a zero-based index, right? So similarly, when it comes to the pay coin transaction, you have a series of coins which you spend, which we destroy, and then we have a series of coins which we create new coins, right? So basically, in case of create coin transaction, you don't have any inputs because you are creating the coins new. But when you transfer the coins, we have some inputs, coin IDs. So 68.1, so the second coin in the transaction 68, because 1 is indicate the second coin, right? Similarly, 42.0 is the first coin from the transaction ID 42, right? So we have series of coins as inputs, and we are spending them or destroying them. And then we have series of coins which we create in them, new coins. So here is the new coins created, 0, 1, 2, 3. So basically, we are with a value of 2.5, 0.6, and 6.4, right? So basically, and we have certain rules saying that the total value of the coins, the consumed coins, for example, 68.1, 42.0, and 73.2, should match with the total value of the coins which we create, right? So for example, if I'm spending a coins worth of 25 bitcoins, and then I'm creating this new coins with the same worth of the coins, right? So that should be valid. And then we have some more rules saying that consumed the coins are valid. So that means these coins are not double spent and not already spent, consumed. And total value of the consumed coins is equal to the total value of the new coins created, right? And again, we follow the same rule. If the coin only can be spent by the owner, so to make sure that all for example, if we have the 3 coins here, all the owners of these three coins. Who are the owners? Basically, basically the people who contain the corresponding private keys, right? Remember, we have this recipient address when we create a coin. So when we created 68.681, there is some recipient address, which is public key. And the people with the corresponding private key, they have to sign it. So we collect all the signatures from all the consumer coins. Then only the transaction is valid, right? So basically, we are making sure that people with who is the owner of the coin is spending coin using the signatures. And we are also making sure that the coins are not already spent. So this is not a double spend transaction. And we are also making sure that the total value we spend is also the total value we create. So that is how the pay coin transaction is valued. Okay. And any questions or comments? This is more or less the basic design of Bitcoin. Of course, there are some subtle differences, but we will go through it much further. So the reason why we are not looking into the Bitcoin transactions and things like that, there are so many internal so many intricate functionalities we have to understand. So that's why we use the very simple the currency with some simple rules to understand those the strength of the underlying append-only ledger and other kinds of things, right? So one of the important thing is, you can see here, what I'm saying is we consume coins, we spend coins, and we create new coins. So in a way, these are nothing but the immutable coins. Here is a question. So what happens if they block with the corresponding transaction ID of the coin, consume coins? Yes. Okay. Let me go back here. This is a good question. This shows that somebody is at least following, right? So that's really good. So here is the question. What happens if one of the consumer ID coin IDs is already spent? Let's say that we have Alice, who is the owner of 68.1 coin, and she has spent this coin somewhere else, transferred to Bob already. And now she is creating a new transaction saying that 68.1, again, using this coin. Remember, we do checks saying that all the coins should not be, unspent, but this check will fail, saying that 61.8 is already spent in the previous transaction, maybe a block somewhere in 72 or something like that, and then this block is not valid, right? So this transaction is not valid. Remember that Squeeze is honest, and Squeeze is only put the valid transaction. So when he receives a transaction like this, he will simply disregard, saying that, okay, I don't buy this, I don't endorse this transaction, put it on the blockchain, because 68.1 is already spent, right? So then it is not valid, and it won't end up onto the public ledger, right? So it won't end up into the public ledger. So that means even the 42.0 and 73.2 coins are valid. They will not be valid as part of this transaction. So these coins will be still unspent. Okay, so we were saying that immutable coins. What is immutability? I think you have Python, right? You know Python and other programming languages. Have you heard about immutability anywhere in the programming languages? Did you hear what? Yeah. So for example, immutable types, right? So can you say what is a immutable type, mutable and immutable type? Let's take simply the Python, right? In Python, what is a immutable type? What is a mutable type? Which cannot be changed. So for example, a string is a immutable type in Python. At least in Python language, it is immutable. So what does it mean? You can create a string, but when you cannot modify the string. When you try to modify the string, tuples are mutable. Good, tuples and strings are immutable. And when you try to change them, then internally the interpreter, of course, it will throw error. But if you try to change the variable value, assign it to a new value, the interpreter will create a new memory location and it will create it. The reason why immutability is adapted is it's very fast. So similar to that, similar to strings in Python, tuples in Python, so kinds are also immutable. We'll see why immutable kinds are important and what advantage it will create. So kinds are immutable. So that means kinds, we can create kinds, no problem. We can spend kinds, no problem, right? So kinds can be created, kinds can be spent, but they cannot be transferred, they cannot be subdivided, they cannot be combined. So what I'm saying is, if you have a kind, you cannot subdivide it, you cannot transfer it. So the only way you do it is, you create a transaction like this, you will spend some kinds. So these are the kinds were spent, and you will create a new kind, right? So the kinds are immutable. But you can do the same effect. For example, let's say that I have a kind, let's say that I have a kind with 6.4 bit kinds, and I want to pay someone 2.5 bit kinds, or you can say I want to pay someone with 2.5 bit kinds, right? So how do I do it? Rather than subdividing this kind, what I do is I will split this kind, I will spend this kind and create two new kinds, pay my friend 2.5 bitcoins, and I transfer the rest of the money to my one of the address which I control, right? So you will get the same effect by destroying the coins and creating the equal amount of the coins. We'll see later what advantage it offers us and things like that. So you can get the same benefit, but the coins are immutable. So now let us try to summarize the squeeze coin. So the squeeze coin is much better than the goofy coin. So it helps us to evade, or it helps us to protect from the double spending problem. So that's really good. Because squeeze coin works perfectly against the double spending problem, because people can see all the transactions publicly visible, which are the transactions valid and things like that. So it is really good in preventing double spending problem. But on the other hand, what is the problem here? The problem is Screws, right? Screws is too much influence, because we are trusting him, and he's the one who is controlling the currencies, and we entrusted him that he can create coins, and he can verify the transactions, and all this verification is done by him, right? So he has too much influence. Of course, what he can do, he can't create fake transactions. For example, he can only create some problems in the currencies. For example, let's say that if Alice has transferred the coins to Bob, and he cannot create a fake transactions claiming that coin which is owned by Bob. What I mean to say is, he cannot steal coins from the people, because to spend a coin, you need the private key of the owner of the coin, right? So in that case, he cannot create fake transactions trying to steal the coins and things like that. But on the other hand, he can do some other damage. So he cannot forge the other people's signatures, so that is secure. That's the reason why we use asymmetric cryptography and things like that. That will make sure that nobody else can spend your coins and things like that. But on the other hand, he can do some damage. He can stop endorsing the some of the transactions from the user, some simple denial of the service and things like that. Let's say that he doesn't like Alice, then he can prevent all the transactions from the Alice, because he's the one who has to put on the blockchain and with his signature, and he will simply ignore the transactions from the Alice, some kind of denial of service, right? And he can also get greedy. He can refuse to publish the transaction unless he gets some tip. I can say transaction fee or something like that. So if people only pay transaction fee, then he will only put it on blockchain and things like that. Or yeah, and then he can get bored of the system and he can stop updating, and then so we have a too much reliance on this who is the central actor, right? So the major limitation of this new design is the screws, because we have one single point of the failure, right? Again, when we saw the last time, I think bit money, one of the digital currency, why it failed was it has a beautiful design and things like that. The company went bankrupt, and because they are the one who is maintaining the ledger and other kinds of things, they went in bankrupt, right? So the same thing. So the critical question which we have is, can we decrucify the currency and operate without any central trusted party? We are saying that Scrooge is the big problem here. As long as he's good and he's doing his duty, we don't have any issues. But on the other hand, when he starts behaving nasty, the thing can go wrong. So our biggest question now is, can we decrucify can we eliminate the screws from this currency design and operate without any central trusted party, right? So this is not easy, because we need someone to verify the transaction. Who will verify the transactions? In this design, since he is there, and who will endorse the transactions? In this design, we believe him, and he is the one verifying the transactions and putting on the blockchain and things like that. So basically, we have a lot of trust in him. And our next biggest question is, can we decentralize that trust? Can we get rid of this guy? So getting rid of this guy means not replacing another person in his place, right? Not replacing another entity in his place. What we are trying to say is, we have a beautiful design where the coins can be created and spent and things like that. All is good and things like that. But can we get rid of this dependency with any central trusted party? Right? He's like a bank, right? So because why do we transact? Why do we believe the transactions endorsed by the bank? Because we have a trust with them. So our next biggest question is how to get rid of the central trust party and decentralize this trust. And is there any way to achieve it? Of course, we don't answer this question as of now, but we will see in the coming lectures how we decentralize this trust, which we have in this trusted within the central party, right? So how we come up with a design where squeeze is avoided and still work in the similar fashion. So basically, we are trying to decentralize the trust, or you can say trustless network kind of thing. So we'll see a bit more into those details in the coming lectures. Okay, now let us look into, let's see how far we are doing time. I think we can still continue. Yeah, so now let us look into this account-based versus transaction-based ledger, right? So I have been talking about the transaction and account-based ledger. So basically, let's see what are the advantages and disadvantages with them, right? So first, let us to understand why we need this immutable coins and transaction-based ledger. Let me take the normal ledger, right? So let's say that account-based ledger. So this is how the ledgers are maintained at the banks, right? So let's say that we have we'll apply the same thing to the digital cryptocurrency as well. So let's say that we have a transaction where LS LS got 25 coins, so create coin transaction, and which was transferred to LS. So that's fine. And then let's say that LS has transferred 17 coins out of these 25 coins to Bob. That's also fine because it is signed by LS, no issues at all. And we can verify that the miners have given the LS the coins and things like that, so no issues at all. And then let us say that we have two more transactions where Bob transferred to Carol 8 coins, right? Because Bob received coins from LS, then he can also transfer to Carol, so no issues with that. So he has 17 coins, he spent 8 coins and things like that. And let's say that Carol transfers 5 coins to Alice. Right? So, and again, all these transactions are signed by the concerned parties, no issues at all. Now, let us say that we have a new transaction saying that 15 coins are transferred from Alice to David. Right? So, my question is this transaction valid? Let's say that this is the whole ledger we have. So we don't have any other things. So we only have a very simple ledger containing 5 transactions, right? The 5th transaction is happening now. So transfer 15 coins from Alice to David. So Alice send a transaction signing this one. And so how do we verify this transaction? To do that, first of all, we need to understand how many coins Alice has in her account, right? So how do you do that? So you go here, you check how many coins she got here. So 25, and then she transfers 17. So 25 minus 17. So she has 8 coins here when this transaction happened, and also 8 coins here in the LIS account when this transaction happened. When this transaction comes, she had already had 8 coins, and there are new 5 coins. So 8 plus 5, 13 coins. So when we get to this transaction, Alice has only 13 coins to her credit, but she is trying to create a transfer of 15 coins from Alice to David, which is not valid, right? But the main point I want to make it here. Let's understand how we verified this one. Of course, this transaction is not valid, but how did we arrive to the conclusion that this transaction is not valid? How did we check it? So you have to go back. You have to start from the beginning. Basically, look into the transactions where Alice has spent some coins, where Alice has received some coins. At least you have to look into all the transactions and see and try to sum up those things and see whether Alice has the balance in her account or not. This is exactly how the banking ledgers works. So, for example, if you have an account at the bank, and they make the account-based ledger, they will keep track of how much money you got into your account, how much money you have spent, and things like that. So there is nothing problem with that, because there is a central authority who maintains this ledger. It is our bank, and they keep track of this inflows and outflows into our account. So it works perfectly fine. I'm not saying that this is a bad design or something like that. But in case of a, let's say, public ledger, we were discussing about having a append-only ledger where we put the transactions and things like that. And in case of append-only ledger, if we maintain like this, we have big problems, right? Because we have to verify, to make sure that this transaction is valid, we have to go from here back to all the way to the first transaction. If the LIS has created the first transaction, got some coins in the first transaction, something like that. So that means you need to scan backwards until the Genesis block, because you don't know which transaction where you got it and things like that. At least you have to do a lot of scans to go further. Let's look into how the transaction-based ledger works, right? With the immutable coins and things like that. When I say transaction-based ledger, it is nothing but the immutable coin design, right? So the coins can be created and destroyed, but they cannot be subdivided and things like that. So now we have a simple structure here. So the transaction specify the number of inputs and several outputs, like what we have seen in the previous design. And you can think the inputs as the coins being consumed, created in the previous transaction, and outputs are the coins being created, similarly what we have seen here, right? Like here. So basically we are talking about this design. So here is we have the inputs and we have the outputs, right? So basically, simplified design. Since this is a create kind transaction, we only have inputs are there is no input because the kinds are created new. On the other hand, these are the pay kind transactions. So you have the input, the kind which we are spending, and outputs to whom the coins have been spent, right? So for transactions in which new currency is minted, there is no coins being consumed, so you have zero, empty value. Each transaction has a unique identifier, and the outputs are being indexed. So as I mentioned before, 20 is nothing but a transaction, nothing but a coin which is created in the transaction ID 2, and it is the first coin, right? So this is the coin. So now let us see how, let's say that we have this transaction-based ledger, how we can verify the same kind of verification. Let's say that LS has got 25 coins. So this is create coin transaction, so we got it. And then LS created a new transaction with ID 2, where she input the coins she got. So she got these 25 coins from the input transaction ID 1, so 10. And remember, coins are immutable. So that means she will now she want to transfer 17 coins to Bob. So she will say that 17 to Bob and 8 to back to herself. So basically, these are the public keys. So this is also called change address, right? And then we have another transaction where input is 20. So that means we go back here, and 0 is second the transaction with ID 2 and first coin. So this is the coin which was created. So we are inputting 17 coins received by Bob. So this is also signed by Bob. So it's a valid transaction. And again, we want to match this input value and output value. So he transfers 8 coins to Carol and 9 coins back to himself. This is again change address. And now we have a transaction, another transaction, which inputs which contain input to 2, 1. So again, transaction with the ID 2. 1 means the second coin. So now we are talking about this new coin created, so which has 8 coins value. And then it outputs 6 coins to David and 2 coins to Alice, right? So basically, this is another transaction. Let's see how this validation is done in the transaction-based ledger with the immutable coins, right? If I want to make sure that this transaction is valid, so how do I check it? So first, I will look into the input. Just 1 second. I will check it to the input of the transaction. Now I'm trying to verify this transaction, right? I will go and look into the input. So the input is 2, 1. So simply I will go to the transaction with ID 2, and 1 means the second coin. Remember 0 base index, right? So I will go here. So the coin is created with a value of 8 coins, and it is transferred to LS, right? So LS is the owner of these 8, the coin containing 8 coins value. So we will see that whether it is the LS who got it. Then we will see if it is the transaction is signed by LS. So the first check is done, and then we will see what is the value of the coin created here. So 8 coins, and then we will see that the sum of the output is also the same. So 6 plus 2, 8 coins. So this is also valid. And to perform a check, what I need to do is I need to just go and verify to the source where this coin is created. So that means you have a finite check of verification of the transactions. You don't need to go to the Genesis block. As long as we know that coins are immutable, so that means coins will not be subdivided and things like that. If we go to the original transaction where you got the coins, and to see that to whom the coin is transferred, to verify the signature is from the same person. So that means it is transferred to LI's public key. So then we expect LIS's signature with her private key. And how do we verify it? You can just use her public key to decrypt, and then you will get the value. So that's the signature verification. So basically, at any point of the time, you just go one step backwards. And then the validation is completely done. So that is the advantage with the transaction-based ledger, because you have only finite scans to do. So at the most, you will go one step. If you have multiple inputs, probably, let's say you have three inputs here, you will look into 3 transactions, and then you're done. So there is no way you need to go back to the till the genesis block and verify, because the functionality, the advantage of such a design is offered by the immutable coin designs, right? So immutable coins and transaction-based ledger. So that's why the verification is so fast. In this case, in the previous account-based design, if you want to verify, then you will spend a lot of time, because you have to go all the way to the genesis block in a design like this. Again, I'm not saying that account-based ledger is bad design or something like that. This is exactly what you use in the smart contracts. When we come to the smart contracts, this is a completely new design. You don't use transaction-based ledgers. In case of smart contracts, you will use account-based ledgers only, because the way the smart contract transactions work is completely different than the cryptocurrencies. In case of smart contracts, you have an account and you have some coins there, and then you perform transactions from there. So we always keep track of how many coins are left over in the account and things like that. So account-based ledger is not a bad design, and most of the financial institutions, they follow this one. And also smart contracts, we use the same design, account-based ledger for the smart contracts, because the operation is completely different. But this is not a good design for the cryptocurrencies, because we need to make verification of the currencies and things like that. Okay, so let's see how we are going with time, and then we can go further. Yeah. So sorry. Okay, so I think we can take a small break, 10 minutes break, and then we get back to the Bitcoin transactions. We'll look into a Bitcoin transaction, and then we'll also look into Merkle tree and some fundamental principles of the hash. Right? So I also included some slides on the hash. Okay, so let's say 10 minutes break. Okay.
Yes, Professor.
Yeah, I will join in a minute. Then I will.